Hi, welcome to BC Video 10.5C Part 2, Elusive Points of Intersection.
Okay, these are the elusive points of intersection. This is not in the textbook. If you can't find all of the points of intersection by solving the original system of equations and using symmetry, use the fact that. So this is a little weird, okay? But the fact is, remember how there's many different ways to write the same point in polar? Well, there are many different ways to write the same equation in polar form. So this is a fact that if you take negative 1 to the power of n, where n is any integer, 1, 2, 3, etc., times r, that will equal f of theta plus whatever that n is times pi. So let's say, for example, you have r equals 1 and r equals 2 sine theta. Okay? What I'm talking about is another name for r equals 1. As you know, is r equals negative 1. But the reason that's true is because of this formula. If I let n equals 1, I have negative 1 to the 1 times r equals f of theta plus 1 times pi, which becomes, since our f of theta here is 1, f of anything is 1, and therefore we end up with r equals negative 1. Okay? If we were to let n equals 2, we'd get back to the original. So you just keep trying 1, 2, 3. It won't take long. Many times it'll only take 2 tries before you're back to the original equation and you can stop. So let's look at the 2 sine theta. If we apply the same formula starting with n equals 1, we'll get the exact same equation. So there is only one version of r equals 2 sine theta. Okay? Let's say, in another situation, what you would do is take the 2 original ones, solve that system. If by observation when you graphed it you're not getting all the points of intersection, then you would use r equals negative 1, which is another version of r equals 1, and unfortunately there is no other version for r equals 2 sine theta. Solving that system should get the other points of intersection. So here's an example, okay? I have these 2 curves. You know how to graph these. One is a cardioid, the other one is a rose with 4 petals. And if you draw it, now this is, you got to be careful here, okay? But if you were to find the tangents at the pole, you'd find that there's a steeper tangent at the pole for the petal than there is for the cardioid. So they actually, the petal and the cardioid do intersect at 2 different points here. So if you count the points, there's a total of 8 purple points of intersection. If I solve the original system, which I did over here, blah, 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 what you will get, believe me, is theta equals about 137 degrees and 22 degrees. So the 137 degrees is this point right here. The 22 degrees is this point right here. So by symmetry, I could get this one, which is going to be negative 22 degrees. And by symmetry, I could get this one, which instead of going plus 137, I'd go minus 137 degrees. But we have these 4 unknown points of intersection that did not come up. So what I'm going to do is take that original equation and use that fancy formula on it. What I end up finding out, this takes a long time, because at this point you're going to have to expand this. Remember, the cosine of a plus b is cos a cos b minus sine a sine b. You will find out that another version of that r equals 3 plus 3 cos theta is r equals negative 3 plus 3 cos theta. So I take that new version of the green curve, keeping the original version of the red curve, and I solve that system. It turns out when I solve that system, I get the other 2. The 49, which is here, and the 118, which is here, and then again, by symmetry, I can get these other 2. Okay? This is more traditional. Find the area inside the limacon, outside the circle. So we find the limacon using our table. The pole did not come up, so I do a separate check, and yes, I do get the pole, so it is a limacon with a loop. If I solve the original system of equations, I'll get pi over 2 and 3 pi over 2. We knew those anyways, because when you graphed the circle and you graphed the limacon, you had those 2 points. So if I just draw the curves themselves, I have those 2 points. What I don't have are these 2 points of intersection, and they did not come up when I solved the original system. So what I'm going to do is I'll leave the first one the same, but instead of r equals 1, I'll go with the easy to find r equals negative 1. If I solve that system, then I will get the two other points of intersection, the thetas for them, which is 2 pi over 3 and 4 pi over 3. Now that's negative 1, comma, negative 1, comma, 4 pi over 3. Okay, so that would be that point there. Now, as soon as I realize, remember what we're looking for, the area inside the limacon, outside the circle. This is the only region that's inside the limacon, outside the circle. It's not very clear. I know you might think it also involves that area, but it does not. I would be clear. I'll probably shade it for you. Now again, easier is to take 2 times, and it's very easy to identify this line. That's theta equals 0 or theta equals pi. Now, I should say easy. However, because this point of intersection here, so if I draw a bigger picture of what's going on, you got to realize actually that the part of that limacon loop is above, that little part right there is above that line that goes through the pole and the point of intersection of the two curves. So as it turns out, since I want just the black area, I'm going to have to take the blue area minus the red area. It's at that point that you realize you can't go from 0 to 4 pi over 3, because that would be going from here, whoops, all the way over to here, and that's not what we want to do. By calling this theta equals pi, which is the same line as theta equals 0, what happens is now we are actually going from 0 pi, because notice that's where we are. We're actually here at theta equals 0. If we go on the limacon, here's where we are at pi over 2. Here's where we are at pi, and we're going from pi to here, which is 4 pi over 3. So be very careful. You really want a good picture to see how that works. Okay, so now we're ready. It's 2 times, because remember we split it in half. There's our 1/2, and then r1 squared minus r2 squared. And that's the furthest away, which is the limacon, minus the closest, which is the circle. So we have that. Okay? So slow down and really have